Alright, welcome everyone. So this video is actually not specifically a lecture wrap-up video per se, but it actually is the lecture that I gave for lecture 8 here on Thursday, April 24th. Again, apologies for the issues with the exam and for those that missed this lecture in class, but that's why I'm recording it, so you'll still have access to it to view on your own time. Alright, so the main course of action for the lecture that we did today was talking about 4 different specific op-amp circuits. So this one right here that we're going to start with is the inverting amplifier circuit. We have the non-inverting amplifier circuit, we have the summing circuit, and a difference circuit, okay? All incorporating op-amps, which again covered the basics of those in the last lecture. Alright, so first thing to kind of just get yourself familiar with is just looking at, what exactly is connected here in this particular op-amp. So here you'll notice a couple of things. Number one is with my 2 inputs, I have one that's tied to this common node, which we're going to basically see assumes that a 0 potential. My other input, which is the inverting input, is tied to some source voltage here in series with a resistor RS as well. And then you have the inverting input tied over to the output as well. And again, remember that this was necessary to keep us in linear region of operation, which is what we want to do for now, because this gives us that negative feedback loop that we need in order to do that. And then the output potential here, again referenced to the common node, is V naught. We've also already indicated the currents that are can be labeled here. So again, IS, current flowing from the source, the IF, the feedback current going through the RF resistor, and then I sub N being the current going into that inverting input terminal on our op-amp. But again, as we had said in the last lecture, we're going to be assuming that that is 0. So a couple of things, so again, the whole point of being able to figure out what's happening in the circuit is to figure out what exactly is the output, V naught, as a function of our input, which in this case boils down to the VS source input here, since that's the one that's feeding into one of our inputs, as the other input is actually tied down to that common node as well without any source of its own. So the way we're going to do this is we're going to first assume we are operating in the linear region of operation for the op-amp, okay? And we're also assuming we have an ideal op-amp. And so again, those 2 considerations allow us to use these 2 relationships that we talked about last time, namely that the inverting input voltage Vn is going to be equivalent to whatever the non-inverting input is, Vp. And then we also again said that In equals Ip equals 0. There's no current that is flowing into these nodes into the op-amp. Again, just another constraint or assumption we had based on the fact that we want to stay operating in the linear region of the particular op-amp. Alright, so how I'm going to go about now trying to get again back to a relationship of what the output voltage is as a function of our input. We're going to look at this node here specifically on the inverting input of our terminal and basically write like a KCL type of expression, but in terms of the resistors and the voltage source that we have here. So first I could say simply that IS plus IF is equal to I sub N. So this is just the straight KCL expression where again I have 2 currents coming into this node, 1 leaving as indicated, as how I've indicated them in this figure here. And so that's IS plus IF equals IN. Then because this node is sitting at a 0 potential relative to the common, the Vn is 0, and that ties back to the fact that Vn equals Vp, and Vp is also tied to back down to the common. From that, we can come up with expressions for Is and If. such that IS is simply VS over RS, and IF is V naught over RF. Okay. So again, these equations can be written due to the fact that the current that is traveling through this resistor RS has to be the voltage drop VS over that value of the resistor there. Again, because we know that the potential at this point here is basically 0 or null. And so the full voltage from this source has to be completely dropped over that resistor there. So that was the IS is VS over RS. And then as far as the current IF coming back here, so now again the only voltage that's being dropped across this resistor RF is going to be the output voltage here, again relative to the common node, because of the fact that again there's no voltage sitting right here at the input to my inverting input. Okay, so then we could plug those expressions back into here, also making the assumption that this I sub n is simply 0. That would lead us then to be VS over RS plus V naught over RF equals 0. Okay, so again, just plugging these relationships into this equation, which is equivalent to 0. And from there, make sure I get this on the video, we would have the output V naught equals negative RF over RS times VS. Okay, so then this is the primary relationship that we're ultimately getting down to, and it is still in your video, so hopefully you can see that. So again, V naught, the output voltage, is going to be equal to negative RF over RS times my input voltage VS, okay? So again, you can kind of now start to see why we call this an inverting amplifier circuit, in that the output is going to be inverted with due to a negative sign with relationship to whatever's coming in on the input. And then it is still amplifying something because of the fact that I have this scale factor RF over RS, which I have control over by, if I was designing this circuit for myself, if I could choose which values of RF and RS might be sitting in my given circuit. Therefore, I can control what's happening with that the scale factor, or in this sense, it's really the gain of this given amplifier circuit. Okay, so let me come over here, talk about upper limits. Okay, so again, kind of getting back to this scale factor, it's the upper limit on our gain, which is that RF over RS quantity. So obviously, as I'm off the video, so obviously could probably think to yourself that there must be some limitation there as to how much of a gain I can really get over my input voltage. I obviously can't use some fixed op amp in some circuit and get infinite amount of gain out of it. So there is in fact some upper limit. And so if we starting out with making the assumption that if our V plus here, which is basically the positive VCC, is equal to V minus the minus VCC, if that's just equal to some quantity VCC, I'll say that's minus VCC, minus V minus. So if the magnitude of the voltages are the same here, but they're again opposite polarities, if those are all the same, we're going to work under that condition, which again I said from last time is not necessarily always the case, but typically makes things a little bit easier. Then, as we know already, the output voltage here has to be less than whatever VCC is. So again, I'm saying here the absolute value of that output voltage must be less than or equal to whatever VCC is, due to the fact that our op amp will eventually saturate, as we again saw on the transfer characteristics that we looked at last time. So again, now plugging that expression into what I have here, that's going to give us that the absolute value of RF over RS times Vs has to be less than or equal to VCC. Therefore, RF over Rs has to be less than or equal to the absolute value of VCC over Vs here. Okay, so this is now defining, again, the maximum, the upper limit of the gain that I can get because this RF over RS value, that proportion has to be less than whatever VCC divided by Vs, our input voltage, is. This is the maximum amount of gain I can get out of my circuit. So therefore you kind of see that if I want to get more gain with some given values of resistors, I needed to either increase my VCC, my input voltage to my op amp, or potentially maybe lower my input voltage as well. But again, then I have a lower signal that I'm working with. So just as an example, if VCC were equal to, let's say, like 15 volts, and Vs were equal to 10 millivolts, then that means that that quantity, so let me kind of erase this here, RF over RS would have to be less than about 1500. Okay, just as an example for VCC, Vs values, kind of maybe some more standard values, and then so this kind of shows you the order of magnitude of the types of amount of gain that we could get out of this particular type of circuit. All right, the little moving magic here again. So I've taken out all the things we worked on for that typical inverting amplifier circuit, and so now I still have the same fundamental circuits. We started looking at an inverted amplifier circuit, but notice the main difference here is that I've removed that feedback resistor. So now I no longer have that tie between the output voltage and the inverting input. Okay, so that really significantly kind of changes the behavior, but as we'll see, it's still going to be an inverting circuit, as it were. So if we do this, the typical term you'll see is this is known as the open loop method without the feedback resistor coming in there. And now this changes the output to be such that V naught is going to be equal simply to minus A times Vn. Because again, now I only have this total input voltage Vn here, simply due to the inner workings of what's going on in the op amp. Is going to invert that input and put that on the output over there. And then we have this other A factor, which again kind of ties back to the previous lecture talking about the internal workings of the op amp, such that this A is this gain factor. And now this gain is a little bit different than the one we talked about previously, which was related to the external resistances. That was sort of like an external gain. This was more internal, specifically to the op amp, and it's going to be, more or less, for what we're concerned about, a fixed quantity for whichever type of specific op amp that you might be using. And so now this is a relationship. So again, we still see that it's inverting the output relative to the input. So now here again, if we assume that V plus is equal to minus V minus, and if both of these are equal to some quantity VCC, then again we know that V in that input has to be less than VCC over A in order to still be in the linear mode of operation. And because we know that I sub n is still going to be equal to 0, no current, 0 amps coming across there, that the drop in this RS resistor due to this fact is very minimal, right? And so therefore, Vn is approximately equal to Vs. And for all intents and purposes, we're just going to say that they are equal. So therefore, Vs, absolute value of Vs needs to be less than VCC over A, again, to remain in the linear mode of operation. So let me maybe come over here. So then a couple of things we can say about that. So if V sub S is less than minus VCC over A, Okay, so if it does go outside of that boundary, then we know that we're in negative saturation, right? Okay. And similarly, if our input Vs gets to be larger than whatever VCC over A that quantity is, then we'll be in positive saturation. Okay. So that's just the main points as far as when you're working in the open loop type of mode. And also just have here on my notes that this A is also kind of known as the open loop gain, specifically because of the fact of how we're operating in this mode, as it were. So again, this kind of wraps up what we're talking about as far as inverting op-amp circuits, inverting amplifier circuits goes. Now we'll get into other types right now. And our next amplifier circuit up is the non-inverting amplifier. I figured I'd go with this one next. Since we just did an inverting amplifier, we could see what the non-inverting amplifier would look like. All right, so you see here kind of immediately there's kind of some obvious differences. So now with the non-inverting amplifier, you see that my source that I have to work with for my input is going to my non-inverting input. So it's kind of obvious. In this case, we're going to call this one VG, and the resistor that goes in series with it to be RG as well. Then we've added this resistor RS connected to my inverting input here. That's back down to my common node. Here I've again reintroduced the feedback, since again this is typically how we want to operate things to ensure we're in the linear mode of operation. And again, still our output voltage is coming from the output from this terminal relative back down to the common node. So now again here, the point is we're trying to come up with an expression that tells us what is this output voltage going to be with respect to our input voltage, in this case VG. Okay, so in this case, we'll start by saying that VP is equivalent to VG. And why is that the case? So again, VP would be defined as between these 2 points here and here. But again, in this case, VP is equivalent to our source VG, because again, that consideration where we said there's no current that's flowing into the input terminals of the op-amp, and therefore there's no current flow through this resistor RG, therefore there's no voltage drop across that resistor, and therefore VP is going to be equivalent to whatever VG is. All right, so then we can also write an expression then for Vn, which again is also equivalent to Vg, because we're still operating under the mode that Vn is equivalent to Vg. And that value specifically, so again, here I guess I forgot to mark this, so it should be plus, and then say Vn here minus. Okay, so again, Vn is between these 2 points right here, and again, because I don't have any current flow here into the op-amp, I can simply use a voltage divider kind of method, because if you look at it then in the fact that I have this resistor here more or less in series with this RF resistor, and then again I have V naught on the output here. So what we can say then is that Vn, which is just basically the voltage drop across this resistor Rs, is going to be equal to Rs over Rs plus Rf. That quantity times the output voltage V naught there. And again, that's just relative. If you kind of maybe want to redraw the circuit a little better to kind of help you maybe visualize things. But again, the output voltage is from this point relative to the common node, and Vn is simply the voltage from this node here from the input relative to the common. And so we can simply use this voltage divider expression to describe that. And so then simply kind of rearranging this to get down to solving specifically for the output voltage V naught would be Rs plus Rf over Rs, that quantity times Vg. All right, so then this is the final expression that we're really looking for to describe, again, the output voltage for the non-inverting amplifier relative to the input, in this case Vg. So again, you see I have no negative sign here. So as explicitly states, I'm not inverting the output relative to the input. But again, I'm still able to amplify my input by this factor now, RS plus RF over RS. And so I could similarly choose my resistor values accordingly. And then we just want to be sure that to stay in the linear region of the curve from the op amp, we just want to be sure that RS plus RF over RS, again, this gain factor here has to be less than that VCC over VG in this case. Okay. So again, this is just, again, defining kind of upper limit that we talked about with the inverting amplifier circuit. All right, and next amplifier up on the docket is the summing amplifier circuit as shown right here. So as you might already kind of assume, it's a summing amplifier circuit because the output is going to be some additive combination of a given number of inputs. So in this case here, a little bit different from what we saw with the inverting and non-inverting amplifier circuits. Here we have multiple different inputs controlled by some given voltage. We're just saying VA, VB, and VC, not specifically going to write out the actual sources themselves specifically. So again, so we're going to be looking for an expression that relates our output voltage V0 to these input voltages VA, VB, and VC. The method we're going to use is very similar to what we've done with the others, in that we're going to look at this specific node right here on the inverting input side and relate that using this V sub n inverting voltage and using sort of a KCL expression again, but again writing each of the currents that are coming out of that node in terms of the given resistors and voltages here. So we could write the first step to that would be Vn minus Va over Ra. So again, talking about the current that's basically flowing into this branch with the resistor R sub A there, plus Vn minus Vb over R sub B, again for the current that's flowing through this branch with the RB resistor, plus Vn minus Vc over Rc, going through the current through the Rc resistor, and then plus Vn minus V naught over Rf plus I sub n equals 0. So again, here, this is the current that's traveling out through this, RF resistor, the feedback resistor that's sitting up there on top. And then IN, again, defined as the current that would be traveling into the op amp itself. Okay, so this is generalized expression, but now, of course, we can break this down using our constraints that we're working with because we're assuming linear operation. Again, explicitly, Vn equals Vp, the two input voltages are going to be equivalent. And in this case, we have a simplifying condition because of the fact that our non-inverting input here you see is tied to the common ground, to the common node. And therefore, that's going to be like a zero potential. So both of these inputs, the inverting and the non-inverting, are sitting at a zero potential. So that'll help us to simplify this. And the other one is with the currents. Again, that IN equals IP, and they're both equal to 0. Again, because no current is flowing into the op amp, again, under the ideal conditions, ideal case that we're working with. So you can sort of see I can already just really be able to get everything I need with this single equation because the fact that, this IN goes away, each of these VNs goes away, again, given those conditions right there. And so what we're left with, as you see, minus VA over RA minus VA over RB minus VC over RC minus V naught over RF equals 0. I could solve this equation for V naught to come up with V naught equals minus RF over RA times VA plus RF over RB times VB plus RF over RC times VC as such there. And so this is our generalized expression relating the output voltage to each of the given input voltages here. So you can see how we're adding the impact of each of these given input voltages, but we're also scaling or using a gain factor for each of the given inputs. And in this case, each of the given gains for the specific input is tied to whatever the value of its respective resistor that's sitting in series with this source over here. Also notice that we are inverting this negative sign. We're inverting the output with respect to the sum of those three input voltages. So again, kind of a analogy or a specific application of this type of circuit could be like with audio mixing type of equipment, right? So where I might have a guitar, a microphone, bass guitar, keyboard, or whatever. So each of those inputs is essentially acting as a source, a potential, because those the signals are being converted into voltage signals. And typically on a mixer board, if I'm plugging all those signals into my generic mixer board, each channel would have a specific gain, which is basically just a variable resistor sitting in there. And so I can tune each given input to raise or lower the volume because I'm giving each one of them a specific amount of gain, amount of boost to that input voltage. And then sitting on my output, where I might be connecting my speakers or my recording module into, I'm simply adding all those input signals together with, again, relative to each of their given gains based on however I'm tuning that in my fancy mixer board, okay? Okay, so now a couple of simplifying cases that we could also sort of explore a little bit is that first one being if each of these given resistors on the input is equivalent, so if RA equals RB equals RC, and I'm going to just use a more generic variable of RS to describe that quantity, whatever that might be, then this expression reduces down a little bit to be just V naught is equal to minus RF over whatever that value RS is times VA plus VB plus VC as there. So again, I'm just saying that if each of these resistors is equivalent, then this, of course, would just simplify down such that I'll only have a single gain factor of RF over RS times the sum of each of those given inputs. And then further, if I were to say that RF, this feedback resistor right here, if that was an equivalent quantity to whatever these resistors were here, then this would further simplify down to just be V naught equals to minus VA plus VB plus VC as there. Again, that's somewhat obvious in the fact that by making this a condition that RF, that my feedback resistor, is equal to each of my input resistors, I'm simply turning this gain down to a unity, and so I'm not getting any gain. I'm simply adding my input voltages, as it were. And that's the basic idea behind the summing circuit. And as I kind of mentioned, this helps you to see, again, we talked about the term op-amp comes from operational amplifier. This is an AND operation that we're able to do. The next circuit we'll look at is a difference amplifier, doing subtraction, similar type of thing. All right, next amplifier circuit we have up today is the difference amplifier, okay? Difference. Okay, so as you might expect, the difference amplifier is probably going to be subtracting some given inputs, putting it on the output of our op-amp. That's exactly what this one will do right here. So again, kind of using a similar analysis as we've done with the others, we'll look at basically writing a KCL expression, but in terms of the voltages with respect to Vn, which is the point right here relative to common as well. So again, we got Vn, in this case minus Va over Ra plus Vn minus V naught over Rb plus I sub n equals 0. Again, this would be that I sub n value, or sorry, I sub n sitting right there. But again, keeping in mind that we're still working again under the constraints that IN equals IP equals 0, no current flowing into our op amp, as well as that the two inputs are at equivalent potentials here, okay? So then what next? So then we can look at defining a relationship for what VP is here. So again, which would be the terminal voltage at the non-inverting input relative to common. And as you see in this particular circuit arrangement here, that's exactly the voltage that is across this RD resistor here. Okay, so now again, keeping in mind we don't have any current flow in this direction, we can basically just sort of look at this given series of components as being in series, all right? And so now we have a voltage source, we have two resistors in series, so we know that VP is going to be the voltage drop across RD, so we could use a voltage divider expression to describe specifically what that value is. So that would be VP is going to be equal to RD over RC plus RD times VB. Okay, so again, this is just the voltage divider equation for what the voltage drop across the resistor RD is with respect to the input, or the total voltage drop across these two resistors, which is VB. So now through some algebra that I'm not going to go through explicitly, we could combine these two equations to a single expression, as well as then solve for V naught, our output voltage. And in that case, we'd come up with the expression that V naught is going to be equal to RD times R, if I write that correctly, times RA plus RB over RA times RC plus RD quantity times VB. So this component minus RB over RA times V sub A. Okay. So again, now you see that our output voltage, again, as described in terms of what's sitting on the inputs, and here there are two main voltage inputs, are VA and VB, is this gain or the scale factor as described by these resistors shown here times VB minus the gain RB over RA times the input VA. Okay, so as you can see, we're taking the difference basically between these two quantities, but making some modification for the specific gain that's relative to each one of them there. Let's see. So we could say that these two scaling factors, they could be equivalent if we have RA over RB equivalent to RC over RD, and in that case, then the output V naught would be simply RB over RA times VB minus VA. Okay, so again, so if I just take this more generalized expression and I simplify it by saying I'm going to make the ratio of RA over RB equivalent to RC over RD, then I could simplify this expression such that the output voltage is simply the single gain factor RB over RA times the difference, again, between VB and VA in this case. So again, this is our more simplified expression under this specific condition, and this equation here is the more generalized expression if this condition is not necessarily hold true. So that is the generalized output of the difference amplifier circuit, and this wraps up our final circuit that we're looking at, and this is really all we're going to cover as far as op amps goes for this course. The idea here is just to give you some exposure to this and at least help you kind of see how these can potentially work in given circuits. And we've basically used various techniques that we've already covered previously, node voltage kind of approaches, using KCL, KVL, keeping all those things in the back of our mind in order to be able to come up with these generalized solutions relating the output voltage to some given input on each of the each of the different amplifier circuits. Okay, so I think that's about all I need to cover as far as this lecture goes. I'll see you all next week. Have a good weekend. Stay classy.